Здравствуйте, Николай
Добрый
Константинович.
вечер. Рад вас видеть.
Взаимно. Только у меня утро.
А, у вас утро.
Recording in progress.
Привет, Саш.
Добрый день. Но что-то со звуком у нас. Обычно это случается, когда несколько микрофонов включены в одном помещении. Или еще хуже, когда динамик и микрофон в разных устройствах.
Устройство 2 у меня, поэтому такое происходит. Сейчас разберусь.
Я понял, это ясно. Да. Это мне нормально интернет.
Саш, что-то вас плохо слышно.
Так, сейчас должно быть все нормально.
Нормально. Просто чрезвычайно высококачественный звук.
Добрый вечер.
Добрый вечер. Да, это слайды вроде показывают, но совершенно пустые. Ну или слайды, а эту доску.
Все так и должно быть.
Так, все по плану, да.
Сейчас еще вроде Томаш хотел подсоединиться, так что сейчас еще можно 2 минуты подождать.
Да-да-да, нет, но и тогда надо будет перейти на английский, конечно.
Да.
Пока вроде баунса нету, и поэтому...
О, это
Очень интересно, почему-то повернулась на угол
чтобы
некратный
народ не
90.
упал, типа.
Саш, вас что-то очень плохо слышно.
Меня?
Да, да, да.
А сейчас вот я вроде говорю, вижу,
Нет, ну сейчас
пробивает.
лучше, но тоже, но тихо довольно, но ничего, стало лучше.
Мы когда
Oh,
с вами
Thomas,
занимались микрофон,
hello, yeah.
и он опять
Yeah,
не работает.
sorry for speaking Russian, I just...
Hi, no problem.
Yeah.
Но если меня плохо слышно, тогда Шень должен с двоих говорить. Поэтому.
No, no. It's especially if you finish eating and start speaking, this will be perfect, I guess. And I will drink tea in.
А так, не лучше. Original sound for musicians own.
Да, стало лучше. It became better, but still there is echo. You should use switch off the loudspeakers. Now, if you use headphones, that should be okay, original sound. But if you use loudspeaker, it's not possible anymore. No, okay. I guess we could slowly start, and then.
Okay, thank you for inviting me. So Sasha Kazachinsky asked me to talk about something simple. Unfortunately,
Yeah, and
there's
for idiots, you should give talk for very simple and explain everything 3 times. Okay.
unfortunately, I was not able to find that much of simple stuff because I'll be my talk will be based on my recent paper with Sasha Sherstov, and well, you know how his papers go. But I'll try my best to convince you in some results. Okay, so what we're talking, what we'll be talking about is computing the rank of a certain matrix and how hard it is. So by how hard, I mean how large is the communication complexity. So we want to split this matrix into 2 parts and give one part to Alice, one part to Bob. So M is partitioned into A and B. Now, as usually,
By partitioned, you mean that just some entries are given to Alice and some entries
no,
to Bob?
I haven't specified it, and there
Okay.
are different ways to do it, but right now I'm talking about the general setting. So then Alice and Bob will, as usually, communicate bits. And in the end, we want both of them. Well, for now, let's say the rank of M. It may be some approximation of rank, but some function of the rank. So how, before we begin, the matrix M will always be from a finite field, n by n matrix. So it will be nice to consider this problem over integer matrices, say with the bounded entries, but the techniques required are very different. So we focus on the finite field because it gives us structure. So how do we partition the matrix? So the first way is to just cut it into 2 halves and say the first half is Alice's input and the second half is Bob's input. Well, you can try to choose any partition, even partition, but that's the most canonical one. And the second way is to partition in the sum. So it's just entry-wise sum of 2 matrices, addition over a finite field, of course. And yeah, Alice and Bob in this case also have n by n matrices. So the second problem is what we call matrix rank problem. And the first problem can be reformulated in something very, very syntactically similar to the second problem. Because this concatenation is not very natural operation. Addition is way more structured. So what we're gonna do in the case on the left, we will say that the rank of this matrix is the maximum number of linear independent rows, or in other ways, it's the dimension of the row space. And what is the row space of this matrix? Well, it's the row space of A plus the row space of B. Okay, so the players need to compute the dimension of the sum of two subspaces. So let's say this is called S and this is called T. And we also note that in the beginning of the protocol, as their first messages, Alice and Bob can just exchange their ranks of A and B. So they can exchange the dimensions of S and T of the row spaces.
So log n bits is okay.
Yeah, it's negligible to compared to, for example, computing. We will be, for example, interested in situations where when the rank is full or constant times n. In those situations, we'll find out that the problem is very hard. So the communication complexity is order n squared. So log n will be pretty negligible. So the cost log n. Okay, so this allows us to reformulate the problem as follows. Alice has m-dimensional subspace S. Bob has L-dimensional T. And the goal is to compute the dimension of the sum. So now this looks very, very similar to the matrix rank problem on the right. So
Yeah, but if you say about intersection, it's clear why they need to exchange dimension S and T. But for some, it seems that they just want to. It's not why exchange them?
I'm sorry, I have a question. Do you share your screen?
yes, I am sharing the screen.
I don't see it. I will try to.
Don't see the screen? Okay,
Yeah.
then we should just stop and try to fix it.
No, I just try to quit and
Okay.
enter again.
No, I am logged in the meeting with both my computer for the video and my iPad for the notes. So you probably
But the rest of people see your screen, as I understand.
Yeah,
You
if somebody
probably-
else has this problem, please say immediately.
yeah, you probably just need
I
to
know.
It seems
choose.
it's my problem, so I try to re-enter.
Yeah.
Okay, so
Wait,
well,
Andrey, I don't understand. So but it's like wait, it's not like the sum. You take the two subsets, you take their union, and you take the linear hull of this.
Yeah, of
The
course.
span,
That's
yes.
just what is called the sum.
This is by definition the sum of subspaces.
Of linear spaces, yeah.
Sorry for idiocy. Okay.
Okay, so these are these problems are well known from the 90s, but so for the problem on the left, we call it the subspace sum. Only very, very special cases were known before. For example, check if two subspaces of dimension n over 2, their sum spans the entire space. Or if two n over 2 dimensional subspaces intersects trivially or not. Only these scenarios. For the problem on the right, it's known that computing the rank exactly is hard, even with the randomized protocols. So this was proved 10 years ago.
Hard means n square.
Yes. So good points. We always have a trivial protocol of cost n squared log the size of the field. So they just exchange matrices and now both know everything. So it turns out in most cases, you cannot do asymptotically better than this. So it was shown for the computing matrix rank. But what about approximating it? So it's known that computing matrix rank is hard. And how did they prove it? Well, they considered not computing the rank exactly because it's non-Boolean function. It's not very nice to work with. So distinguishing the cases full rank and rank less than n. So basically determining if a plus b is non-singular is still hard. So
Excuse me, do I understand correctly that that holds for every field?
what exactly holds?
Lower bound or upper bound?
The lower bound. And square log f.
It holds for any finite field, yes.
Uh-huh.
So this was from 2012. Okay.
Do they reduce some known problem to that, or they have some direct proof for that?
No, it's direct proof. And then, so they prove from a randomized case. And then I thought, maybe there is something simple proof for deterministic case, at least for non-singularity. Because it will be nice if we can easily prove at least something about non-deterministic complexity. Well, I couldn't find, and I couldn't prove it very, very elementary using some nice like fooling set arguments or something like that. I have a proof that is not too complicated, and I'm gonna start with this, but I don't know very simple proof, and I think it would be nice if someone could do that, but I guess it's not super important because yeah, we're gonna see some proof.
No, I mean it's fine. Yeah, let's try to understand, I guess, because yeah.
Yeah, Sasha, you still have echo.
Sorry.
And do you mean that for both setting we have that lower bound?
Yeah, so before our work, this was known, and so if we just want to approximate up to a constant factor, so this was nothing was known for this, and nothing was known for subspace sum in terms of the general case, only very special cases. So we do determine complexity for both situations, and the techniques are, so the skeleton of the proof, the high-level idea is the same, but the left case, as you can imagine, because you need to deal with intersecting and taking sums of subspaces over a finite field, it becomes very technical and very complicated. So some steps that are pretty much obvious and very well, we get them for free in the matrix rank case. They become pretty complicated for the subspace sum problem. So yes, we solve both this and this, but now I will, if you excuse me, forget about this problem.
Just before you forget about this, let me check
Yeah.
that I understand correctly. So imagine that S and T just are one-dimensional spaces. So then we
Yes.
need to check whether they are the same. And this is somehow equality. So we get lower bound n, yeah? And the problem is to get bigger lower bound.
Well, if they have the same dimension, and we want to,
No, just one dimensional. The most simple case what I can imagine. We have two vectors, and then dimension of their sum is just either 1 or 2, depending on whether the vector for F2 are the same.
yeah. That's good point. So when they have, it's in general we have this like degenerate case if they're both if both dimensions are equal, then it may be actually equality testing, and then there is constant cost randomized algorithm.
But no deterministic. So deterministic lower bound is obtained in this way, or not.
We actually didn't think about deterministic at all.
Well, Sasha, you obtain only linear lower bound, deterministic, yes.
No,
But
if we consider
you want
spaces,
N-squared lower bound.
if we consider spaces of dimension n over 2, then we can check whether they are the same. And I guess that we have a lot of these spaces somehow.
But it's not an equality test.
It's inequality test for subspaces, because the sum has the same dimension if and only if the subspaces coincide. No, that's what I think Andrey said just few minutes ago.
Yeah. So when we formulate this problem in terms of the Boolean problem, we want to distinguish between cases dimension of s plus t equals to one value versus the other value. Or if we want, so this is a promise problem. We only need to distinguish these two cases. Or if we want to check if the dimension of s plus t is at most d. So when we have m, l, and d all equal, so we have subspaces of dimension 10, and we want to check if their sum is at most 10. This can only happen when they coincide. And then it becomes equality testing, yes.
And the number of subspace of size n over 2 is quite significant. So we get some non-trivial lower bound, I guess.
Yes.
Yeah.
Yeah, their number should be n squared. I mean, 2 to the n omega n squared. So we get in this way n squared lower bound.
Okay, so sorry for this digression. Yeah.
Okay, I may talk about the actual lower bound later if there's time, but I don't want to discuss that case because it doesn't provide any new insights, but it's very, very complicated at some points.
Okay,
So,
sorry. Just
yeah.
forget about it.
So instead, I will focus on the matrix rank. Okay, so before we proceed, I want to just list all the facts and definitions that I might need later. Okay, so we will be using Fourier analysis, and for that we define the inner product of two functions that are in general complex valued. It's just standard inner products, and we take the complex conjugates of one of the functions. Sometimes people define it as an expectation.
The functions are defined where? On some group or what?
Oh yeah, good point. It will be well in general here we can think X is just finite set. So sometimes people also divide by the size of the domain to get to treat it as expectation. For now, we will just use summation. Okay, for two matrices over finite field or over reals, their inner products is just inner products as if they're vectors, or it can also be written as a trace of their product, of their multiplication. Okay, a very basic equality for the inner product of matrices. So basically you can always transfer matrices to the other side of the inner product by transposing them. It follows from the cyclic property of the trace. Okay, and we will need some matrix norms. So any n by n matrix M, it has a singular value decomposition. It's decomposition of this form U sigma V star, where so V star it's conjugate transpose, and both U and V should be unitary. So the product U with U star is identity. Well, in particular, U and V will be full rank. But what's more important is what sigma, it's a diagonalized matrix with singular values on the diagonal. So they will be non-negative, and they can be alternatively defined as square roots of eigenvalues of M conjugate transposed.
But now the matrix is real or complex or what?
Oh yeah. So this holds for any real matrix, but the singular values will be positive real numbers.
Yeah. So U and V are orthogonal. You just say unitary. That's why.
Yeah, unitary for complex value matrices, and for real value matrices, they're orthogonal. Yeah.
But for complex value matrices, we also have such a thing.
Yeah.
So, okay.
Okay. Now we have the very basic norms of the matrix. So the spectral norms is the largest singular value. Then the most important one for us will be the sum of the singular values, which is the trace norm. And there is also Frobenius norm, which is like L2 Euclidean norm when you treat the matrix like a vector. But what's interesting about this norm is its invariance under unitary transformations. So if we consider singular value decomposition and take the Frobenius norm of the of sigma, it will be the Euclidean norm of the vector of singular values. Okay, any questions up to this point?
No,
Okay,
it probably should be true. So let's see how it's
Yeah.
used.
So one thing that is a little less well known, but it's very, very natural, is some facts about random matrices. So I will use this notation M sub n for non-singular matrices over finite field. So it's a finite set. And in particular, M and MR, it's n by m matrices of rank R. Okay, so two facts. If we have some fixed invertible or non-singular matrix, and we multiply it by uniformly random non-singular matrix, either on the left or on the right, both products will also be uniform. Why? Well, because this map
Well, that's a
X
group.
mapped to
Yeah, it's a group seems to be. And,
Yeah.
We just make a shift. So this is
yes.
okay.
So this is just automorphism, and it's pretty straightforward.
Yeah.
Another fact is if we have rank R matrix, and then we multiply it by independent matrices that are uniformly distributed on the non-singular matrices, we will get the uniformly distributed rank R matrix.
Yeah, so it seems that when we multiply by one side, we get a random image. We just
Yes.
change the image, and the other side we change the kernel, and so they are both changed independently, and it looks very plausible.
But if I just multiply on one side, I mean, this should also be true, no?
No, because
So just
kernel is the
X times
same.
M.
If you multiply on one side, you just for a fixed matrix, then you keep unchange the kernel or the image depending on the side. So you cover only small part of all matrices with given kernel. No, we apply an operator after a matrix, so kernel we cannot change the kernel. If we want to rotate kernel also, we can change only image, and
Yeah.
so
Well, you can see that if you have a matrix M something like this, if you multiply it on one side, you will either never get 0 columns on the right or 0 rows on the bottom. Okay. So another thing that we need is Fourier analysis. Okay, for this particular section, I will state it with the field of size P, where P is a prime, just for simplicity, but it can be easily extended to Q. Okay, so omega is just a primitive root of unity, so it's a complex number of length 1 and angle 2 pi over P. And the most important thing about it that we need is that if we sum the powers of omega over all elements of the field, we will get 0. Well, pictorially, it means we consider all powers of this vector, which are just rotations by the same angle, and we sum them as vectors, and the sum is 0. Okay, now, so we will be working with matrices, so we need to define characters for the matrices. So these functions, he sub a of x, defined as omega to the power negative inner product of ax. So ax are matrices over fp. So this is some integer from 0 to p minus 1. And then we raise omega to that power, and we will get some complex number. Okay, why do we need them? Because they satisfy the following property. So the character at matrix x plus y, if you substitute x plus y here, because of the linearity of the inner products and exponentiation, we will get this product. And what do we do with it? Well, we consider the product of, so these characters are functions from n by n matrices to complex numbers. So what if we consider their inner product as functions? Well, we just, it's the sum over all matrices, all n by n matrices X. The product of the functions where we take complex conjugate of the second function. So we can rewrite it as this. And now we need to observe that if b is equal to a, this is 0. So it's the exponent is always 0. So we're summing ones. And how many do we sum? P to the n squared. Okay, if a is not b, then this is non-zero matrix. So here we get some non-trivial linear combination of elements from X, and it's not hard to see that in such a case, if X goes over all the matrices n by n matrices, then because of this property, we will get 0.
So in terms of group, we just consider a group of p elements and then take its n squared power and consider Fourier analysis on this group.
Yeah,
which is matrices.
that's exactly what happens.
Yeah.
Okay, how we extend it to Q? Well, we consider any isomorphism between FQ and the additive group FPK.
Since we don't use multiplicative structure yet, it's just several copies of FP. Yeah,
we can write them in Z. And then we say that if A is from FQ, we say omega to the A is equal to omega to the x1, omega to the x2, omega to the xk, where A is mapped to this vector x1, xk. And then the same holds. Okay, so what this gives us is that these functions form the basis of the space of functions from n by n matrices to complex numbers. In particular, we can express any function as a linear combination of these character functions with some coefficients. So these are Fourier coefficients indexed by matrices. And when we know f, how do we compute a Fourier coefficients? Let's say f hat b. So we just take inner product. So it's I'm answering Sasha's question in the chat. We are summing over all n by n matrices. So this will be just the number of n by n matrices. So each component is from FP, and there are n squared entries. Okay, so to compute the Fourier coefficient indexed by B, we will simply take inner product of f with the character, then represent F using this linear transform, then use linearity of the inner product, and the fact that we prove that these are orthogonal for distinct A and B. So the only remaining term will be the inner product of he sub B with itself, which evaluates this. So we get the formula for Fourier coefficient. Okay, this should be pretty standard. All clear so far?
Yeah. When you start using it, probably we will start asking again, but still.
Yeah. So, okay, I will probably continue with the actual lower bound for the randomized case maybe next time. And we will need a lot of things, but we will not need any very, very complicated facts. So from the Fourier analysis, this is probably the only thing that we need as far as I remember. Okay. So let's try to see why deterministic computation is hard. So we have two matrices A and B, and we need to distinguish whether their sum is full rank or not full rank. Okay, we, as usually, the first thing that we do is we consider communication matrix. So for now, let's consider Boolean communication matrix. So we simply, this is a communication analog of the truth table. So it's indexed by matrices A and B, and for the AB entry, we simply write the answer. So it should be 1 if rank of A plus B is n, and 0 if it's less than n. So the order of this matrix is the number of n by n matrices, which is q to the n squared. Yeah, from now on, we go to the general finite fields. And because all the Fourier analysis that I mentioned above, it holds for any finite field. Okay, so we will use the rank lower bound. So we want to show that the rank of this matrix is large.
Large means proportional to n squared log f, yeah?
No, the rank should be q to the n squared because the deterministic complexity is lower bounded by log of the rank.
Yeah.
Okay. So, okay, usually what you do for the rank, you, for example, can multiply it with itself, like we did for inner product. But here we need something more powerful. We will use the definition of the rank using singular values. So the rank of M is the number of non-zero singular values.
When we consider as a real matrix.
Yeah, so this matrix M is Boolean matrix, zeros and ones, and we treat it as a real matrix. So there might be some confusion in the way that we have matrices over finite fields and also matrices over reals. So yeah, this is a real matrix. Okay, the first lemma is very good on its own. So this is from the paper from 10 years ago about randomized complexity of non-singularity of this problem. But maybe it was known even before. So if matrix G is such that its entry AB is defined as little g of A plus B. So it's exactly what we have here. All the entries depend on A plus B. So in this case, the singular values of G, including multiplicities, are q to the n squared times G hat of X, where X goes over all n by n matrices. Okay, how do we show it? Well, let's just apply Fourier transform for little g. So the entry AB of the matrix G is little g of A plus B. Now we write little g as the sum over all matrices G hat of X omega to the negative inner product X A plus B. Okay, now we again break down this omega into two. And okay, that's pretty much the whole proof. It will become the whole proof if we understand how to write it in the matrix form. So okay, this is our matrix G, and we're calculating its entry AB. So let's consider the following, the product of the following three matrices. So I want to just write this equality in matrix form. So the left matrix will be omega to the negative AX. So it's row indexed by A. It will have elements omega to the negative A product X1 all the way, omega to the negative product A with X Qn squared. Well, this is some order on the matrices. Okay, then what comes is the Fourier coefficients. So it's a diagonal matrix with G hat of X1, G hat of X2, G hat of X Qn squared. And the last matrix is, well, the same as the first one, except it's transposed. So here the column indexed by B will have all the necessary Fourier coefficients. Okay, so what will be this entry? And yeah, the middle matrix is diagonal. So the entry A plus B will be precisely this row. Elements of this row multiplied by the diagonal entry-wise, multiplied by the column, and summed together. Is it clear? Yeah, that's what I wanted to ask.
No,
Okay, so
it's just no. Frankly, I just it should be checked. It's difficult to follow that everything is exactly like this, but the plan is clear. So if it's just we have this decomposition with unitary and diagonal matrices, more or less. You say that it's exactly the given by this G hat things. So
yeah, so what happens when you multiply, let's say, these two matrices? You take the left matrix and multiply the first column
It's
by this.
this should happen. So if you no, it's easy to believe that probably you are right and everything fits, but
Yes,
I
so
won't make it bet right now. But okay.
yes, so this looks almost like a singular value decomposition. Except that the matrices on the sides are not necessarily unitary.
They are not made by characters, and therefore.
Yes, they are.
But then they should be orthogonal, no?
Yes, they are. But the product of the vector with itself should be
not one, but some constant.
Yes.
Yeah.
So right now it's the products of the character with itself, which is q to the n squared. So to get them orthogonal, we need to multiply this by 1 over q to the n squared over 2. And this by 1 to the q to the n squared over 2. So the middle one will be multiplied by q to the n squared. Okay. So now we need to compute the Fourier coefficients of our function that defines the matrix. So in our case, G of the matrix M is 1 when the rank of M is n, and 0 otherwise. So we need to compute G hat of M. Okay, this part will be somewhat technical, but I think we need to do it for the sake of completeness, because I don't just want to pull it out of the hat. Okay, so let's just start calculating it. So what is a Fourier coefficient? It's an it's q it's 1 over q to the n squared, inner product of G with a character. So let's just write it out. So G is an indicator a function of the matrices of full rank. So it means we're just taking summation over matrices of full rank. That's what That's what G does. Okay, now let's go and turn it into an expectation. So now X is a uniformly random matrix of full rank, and we need to compute the expectation of this. Okay, the first
It will
observation.
be non-zero for every M, or it will be, or you will just show that for some special M it's not zero, and there are many of them.
It will be non-zero for every M.
Okay.
So for actual lower bound for the randomized complexity, we will need the actual values of these Fourier coefficients. So we might as well calculate them now. Okay, so the first observation is that this thing, this expectation, is equal for matrices of the same rank. So if we have matrix N such that the rank of M is equal to the rank of N, these expectations will be equal. Why? Because we can write N as P M Q. Then we will use that property that where we can shift matrices on the other side of the inner product. And then the matrix P transposed X Q transposed, when X is uniformly random, full rank matrix, and P and Q are fixed, then the products will be also uniformly random, non-singular matrix. So for matrices of the same rank, for matrices M, so this depends only on the rank of M. So we can then take the expectation not just by over X, but also over M, which will be uniformly random N by N matrix of, well, let's say this has rank R over rank R matrices. Okay, this expectation is very, very important for us. So it will be parameterized by two things. So I will use subscript N not to confuse it with the gamma distribution. So we have two parameters. The first one is the rank of matrix X, and the second one is the rank of matrix M. So the expectation is given over matrices X of this rank and matrices M of this rank. So in general, N is not necessarily N. It can be any rank. But for now, we only need this expectation when one of the parameters is N.
Yeah. So you say that it doesn't depend on M, but it could we can expect that for next you can take just some specific M for which is easy to compute. But
Yeah, yes,
that's not
precisely.
what you do. You do averaging over all M instead.
Yeah, yes. So I use this property that's the values of expectation are the same for same rank matrices in two ways. One, to average, and this will become useful for the general values of the gamma function, but also to substitute m with something nice, and I will write it here. So this expectation is so what's the nicest matrix of rank R?
Probably ones on the diagonal and zeros,
Yeah.
no?
Yeah, exactly. So it's the expectation over X omega to the inner product of X and this matrix. Okay, I will also remove the minus sign, because if X is non-singular, negative X is also non-singular, so it doesn't change the summation, the expectation. Now, what is this product? It's just a truncated trace. So the inner product of X and this I sub R is the element-wise, entry-wise product of X with I sub R, and then adding the elements together. So it's just these first R diagonal elements of X. So this is the expectation over X, omega x11, sum all the way to XRR. Okay, now we will do maybe somewhat not obvious thing. We will introduce another matrix into the expectation. So X is still a random non-singular matrix, but we will multiply it by random non-singular matrix, which is lower diagonal. Meaning that for L, we have something on the diagonal, and above everything is 0. Okay, that's what we have now. This again works because when we multiply by random, so if we consider fixed L and then multiply it by random X, the product XL will be distributed as a random, uniformly random non-singular matrix. Okay, any questions up to this point?
So L is fixed, you don't average over L, just
No. Even for fixed, the expectation will be
is
the same,
yeah.
but then when we average over L as well, it's still the same.
So what you write in, you mean the average in this is your notation? Yeah.
Well, I mean that's L is also random.
Also,
matrix.
yeah. Mm-hmm.
Okay. Why is it useful now? Because we can fix X and compute the expectation for fixed X, and it will be much nicer. So we can take expectation of X, and then the inner expectation will be for fixed X. So the same thing, but for fixed X. And now it turns out that this is much simpler to compute. So yeah, let's focus on this. We will say that X is nice if it looks like this. So for the first R rows, everything after the main diagonal is 0. Okay, now we will compute this expectation, the inner one. First for cases when x is nice, and then for first for cases when x is not nice, and then for cases when x is nice. Okay.
So when x is nice, it should be 0, no? Because just everything is independent and it's just a product, no? Or
When x is what?
when x is nice, it should be 0, right?
Well, actually, it's the other way. When x is not nice, it's 0. Okay, let me.
Okay, L is a lower. L has zeros also in the same like. Okay, yeah, I don't know.
So L looks like this. So these are non-zero elements, zeros here and anything here. So what's the distribution of the entries of L? How to generate a random non-singular lower diagonal matrix? So I say that all these diagonal elements are independent and uniformly random non-zero elements of the field. You have to have them all non-zeros, the diagonal elements.
Yeah.
And once you fix them, the sub-diagonal elements then can be anything. So the distribution of elements of L is the following. All the entries are independent. The diagonal elements are random non-zero elements of the field, and everything below diagonal is uniformly random. So what it means that x is not nice. It means that somewhere here there is a non-zero element. Okay, so we, in our expectation, here we have the sum of diagonal elements of the product. So we are interested in the sum of these elements. So when we have in row J non-zero x, then what will be the distribution of the jth entry in the product? So this jth entry is the product of the jth row of x and the jth column of L. So this element is non-zero. And what will it be multiplied by? Arbitrary element in the field, uniformly random. So this inner product will be uniformly random elements of the field. Okay, and now we are taking the sum of these diagonal elements. Well, it's enough that just one of them is uniformly random. It means that the sum of these truncated diagonal is also uniformly random. So in our expectation, the exponent is uniformly random. So if X is not nice, then the expectation in question is the expectation for over random elements of the field omega to the A. And this is 0. Makes sense?
think yes. I don't know, but what about others? Sasha,
Oh, again, I see the mechanism, but I cannot check that everything is.
No, I mean, so far, I think, let me just say once again. So we have this thing, expectation of W to sum of the elements of L, the matrix L, with coefficients that are given by matrix X. And in matrix L, all elements are independent. Diagonal elements are non-zero. I mean, they are like uniformly random from non-zero elements. And elements that are below diagonal, they are uniformly at random in the whole field with zero.
Yeah. So the distribution on L is simple, and we use this. Yeah.
Yeah, and then we have this W, and then there is some linear form in the elements of L. I mean, in the sense there are elements of L with some coefficients that are from a fixed matrix X. And X is nice if and if we take this thing that's like the trace the first R elements on the diagonal, then there will be like these elements of L from the diagonal, the first R with coefficients in X, and there are also like elements from below, but if there are any element in this linear form for L.
So just one non-zero element makes everything uniformly distributed.
Yeah.
That's the main
so the only
main
case
point.
when it's
But
not zero is when X is nice. It means when so indeed there's all the things to the right on the diagonal in the first R rows is zero. When it zeros all potential these things that are uniformly at random in the whole field.
okay.
And then we have either the like products of so it can be zero also, right? And it can also be W, the root of unity to to a non-zero elements to the like to a random non-zero element of the field, and this is non-zero because the sum of all things. It's like minus root of unity, I guess. No, wait. Yeah. Yes. Oh, sorry, at -1. Sorry, I say stupid thing. So yeah. So there will be some zeros and some ones and some minus ones.
You mean in the case when X is nice?
Yeah. So when X is nice, do you say that there will be like a -1 to the number of non-zero elements on the diagonal of R? This thing.
Yes, there will be -1. Almost. Yeah. Let me just. Okay. If X is nice, so what? So we are interested in these elements on the diagonal, which each element is the product of the jth column of L and the jth row of X. So because for the X, the tail is all zeros, but for the L, the beginning is all zeros. The only surviving element in this inner product of row and column is the diagonal elements multiplied. So in this case, XLII, so the oh, should I say J. So the J diagonal elements in the product of interest is just the product of xjj and ljj. So we know that this thing is uniformly random non-zero element. So what about the x? So x is nice, but recall that x is still non-singular. So if x is nice and non-singular, these elements on the diagonal have to be non-zero. And analogously to L, it's not easy. It's not hard to see that they're uniformly random non-zero elements. So each entry on this little diagonal of x is also a uniformly random non-zero element.
But wait, what does that mean? It's a fixed matrix. It's just a fixed matrix. Xjj just are fixed numbers that are non-zero. I mean, because we are considering well.
Oh,
X
yes. Yes. Thank you. So it's just enough to say it's non-zero. So we have random non-zero element, and we multiply it by a fixed non-zero element. So the distribution of this product is a random non-zero element. Okay, so the last thing to note is that the columns of L are independent as random vectors. So these diagonal elements that we're interested in are independent. So the expectation over L of omega to the sum of xLii for fixed x, this can be broken down into the product of expectations. And where each is just xLii. Because diagonal elements of XL are independent. Okay, and we just established that this thing is uniformly random non-zero element. Okay, so in this expectation, if we just write it down, it's how many non-zero elements? Well, 1 over q minus 1. And then we have a summation omega to the a for non-zero elements. So this is just, as Sasha said, summation of all elements omega to the a minus 1. And summation over all powers is just 0. So the whole expectation becomes minus 1 over q minus 1 to the r. Any questions before we move on?
No, I have a kind of philosophical question. So it seems that this computation somehow there are no very non-trivial step. Each step is trivial, but just when you look at the statement, it's just for you it's a kind of a routine computation that confirms something that you already expect, or it's a quite an unexpected observation which for some strange reason is true. How it looks like.
I think that the statement is more or less believable. The calculation I mostly show so that we have the sense that we actually proved some lower bound. I think that this calculation is very, very nice. It's much better than what I first came up with.
So it's just a very improved, cleaned version of something which existed before.
Yes, yes.
Yeah. And so you started with the set characteristic function of the set of metrics of full rank.
Yes.
And
we're
just a stupid question. If we consider a set of matrices of some rank, it will also have kind of explicit Fourier transform, or it's just a very rare occasion that full rank is quite special set. Why it's
oh yeah,
kind of intuition for this Fourier transform. We can compute it more or less for everything, or just we are extremely lucky to get something.
Yeah, that's a good point. So right now in our communication matrix, we have zeros when rank A plus B is not full and ones when it's full. So that's why we're computing this Fourier transform. But when we try to solve the general problem, which will be distinguishing rank K versus rank N, we will have values 1 when the rank is full and -1 when the rank is K. And we will have to compute similar Fourier transform but for the indicator function of the rank K matrices. And that's when we'll have the general case of the gamma function. So we will need this expectation.
But in fact, the fact that in this distinguishing case, you don't know which values you should have for the matrix of intermediate rank, still you somehow compute the Fourier transform for matrix with arbitrary values there, or how it can happen.
Yes, I will talk about it later.
Okay, yeah.
But for now, answering your first question, yes, we will need to compute this expectation when the matrix M is matrix X is also a random matrix of fixed rank, and it will not be closed form formula like here. So here we can compute exact value. For the other case, we will be able to use these special case values to show certain properties of the general values of the gamma function. But yeah, no closed form solution. Okay, so we calculated the probability, the expectation of interest for not nice matrix, it will be 0, and for nice matrix, it will be this thing. So this is this expectation in the box, and what remains to show is the probability that X is nice. Okay, so the probability, yeah.
But just to show that it's non-zero, it's already done, no? Because I mean, it's just the same thing for every X.
Yes. So for the deterministic complexity, we are done.
Okay.
I will just.
But I mean, you say that somehow we need to compute them for the just for the randomized case.
Yes, later next time we will need the actual values. Okay, so the probability that the random non-singular matrix is nice. Okay, so how do we calculate it? So it will just be the number of nice matrices divided by the number of non-singular matrices. Okay, so how many non-singular matrices are there? So
No,
if we want
just the first vector should be non-zero, the second should be not in the space, yeah?
yes, so non-zero, it means, so q to the n, that's the total number of vectors. So non-zero means this many. Then we pick any vector which is not in the span of the first one,
Yeah.
and so on. So the last vector will be any vector not in the linear span of the first n-1 rows.
It's q minus n minus 1, should, yeah.
Yeah. And how many nice matrices? Well, let's also start constructing it top to bottom. So the first row is any row such that this element is non-zero. So it's q minus 1. The second row is the diagonal element is non-zero.
So there are non-zero elements and some zeros which we need to choose, and some arbitrary elements, yeah?
Yeah, so all these are arbitrary. So yeah, we can just write q minus 1 to the r for these elements on the little diagonal. Then for the sub-diagonal will be q to the r choose 2. And the other n minus r rows, so this part, it will be the same as for the non-singular matrices. So it's just q to the n minus q to the r all the way to q to the n minus q to the n minus 1. Okay, so that's it. So we need to multiply this by the expectation when x is nice. So the gamma function will be minus 1 to the r, q to the r over r choose 2, divided by q to the n minus 1, q to the n minus q, all the way to q to the n minus q to the r minus 1. Okay. That's the gamma function, and the Fourier coefficient that we started with is this quantity multiplied by the gamma function. So in particular, we see that they're all non-zero. So that matrix we started with, the communication matrix,
Has full rank.
has full rank. So the deterministic complexity is actually, well, maximum possible, essentially. So it's
And
not just...
even if we have a splitting into rectangles, then the number of rectangles is...
Excuse me, can you sum up why the rank is full of that matrix?
So the
Because
rank...
all Fourier coefficients.
Okay. all Fourier coefficients are non-zero, right?
Yes.
And why is this?
Because there was a formula, all this long computation,
Yeah,
get
Yes.
some,
I
get
want
some
to see.
non-zero answer.
It's had G of M, what we have calculated, but at some time we had zero, I guess, in the calculation when the matrix is nice, right?
No, it's not. A matrix is nice. There was an averaging over all matrices, over
Okay.
all x's, and this averaging was split into part, into nice x's and not nice x's. And
Yes.
so we just ignore the part when x is not nice and took
Right.
average only over x's which are nice. And the problem is how many of them we have, and this is computed and so on. So it's not the case for the coefficient. It's just
and the point is
part of the sum.
For nice matrix, the value is the same for all nice matrices, right? I see. So
Yeah.
nothing cancels.
Yes.
Yeah, no. I can feel only that I'm ashamed that I'm so unfamiliar with this Fourier transform and computation. It probably for people who know this should be some kind of obvious. If you know what to do, that all this should be somehow easy. But for me, it's a complete miracle. Why things are so arranged in such a simple way and strange. But what can? And finally, you know the matrix has large rank, and if the matrix is split into combinatorial rectangles, they have rank 1, so we need many of them, so we cannot do less than. So we get a without any constant, we get just a bound.
Yes.
Exact.
Okay. Now I wanted to switch to randomized communication and say something about it. So how much time do I have?
No,
Like,
it's actually exact. So this is 1 hour and a half, and so if we want, it's very good time to split, to make a split between this and next meeting. If you want to say something small, then of course you can continue as long as you wish. But if there is no new part, maybe it's logical to postpone it to the next Monday.
Okay. I wanted to go to randomized communication, and for that we have an upper bound and a lower bound, and I want devote the whole next talk to the lower bound, but the upper bound is I can just state the protocol, and it will be very, very easy to believe. So it will take like 5-10 minutes.
No, 5-10 minutes is completely okay, but probably then people will start next time will start asking question about upper bound, and so you didn't succeed in your desire to split it. But let's tell the protocol.
Okay, so yeah. So we just proved that randomized complexity of non-singularity, deterministic complexity of non-singularity is full. It has been proven that the randomized complexity with bounded error is pretty much also maximum possible up to constants. And it was also shown that promised problem, when we just need to distinguish ranks n-1 and n, also maximum possible randomized complexity. So none of that applies to approximation. So for approximation, we need some more general statements.
But
so
all these are lower bounds, yeah?
Well, yes, they match trivial upper bound when the players just exchange matrices. Yes. So to study constant factor approximation, we need to solve, we need to get strong lower and upper bounds for these two problems. One is distinguishing if the rank is at most some little r. That's the total problem. And we want good upper bound. Or distinguishing two values of the rank. So we want lower bound for that. Why so? Well, if we have approximator, it will for any for true value of rank, the approximator will give us something in the neighborhood. And using this, if the values are sufficiently far from each other, for example, constant times n and n, we can run the approximator and distinguish between them. So if we have approximator, we can in particular distinguish between rank Cn and n. So if we can prove lower bound for this partial problem, it will, if we can show that it's strong, in particular, the distinguishing Cn versus n is omega of n squared log f, then it will mean that constant factor approximation is hard.
And if
So
you
we
want to distinguish 0 from n, it's easy. You say Cn, but just stupid question. Not 0, but 1, or I don't know. Why Cn? It's essential, so that it's still not very small.
Well, because if we have approximator, then we have do this, distinguish Cn and n, and distinguishing Cn and n, it's hard.
But distinguishing 1 and n is hard or not?
No.
Ah,
When
so
you decrease little r, the communication
if r
complexity
is small,
drops.
then yeah, that okay.
Yeah, so what we show is that we have an upper bound for the total function on the left, which is a harder problem, harder for protocols. So we show that the randomized complexity is r squared log f. This is a very simple protocol. But on for the problem on the right, we show that the randomized complexity is the same. Okay, but it would be pretty good if we just had this. This would mean that they match exactly. So both problems, the partial one and the total one, have the same complexity. But it turns out that this bound holds even if the error is very close to 1/2. So I think it's r over 3, something like that. So if it's just a little better than a random guess, and we just need to distinguish, let's say, Cn from n, we still need to do full trivial protocol.
Okay, so that's very more than full answer to the question somehow.
Yes.
And so you now you promise to give a simple protocol for the upper bound.
Yes, right here. So yeah, let's say we want to distinguish at most k versus larger than k. I don't know why I switched to k, but in the proof somehow we use k. Okay, so we have Alice and Bob matrices A and B, n by n. Now they generate matrix k plus delta by n and n by k plus delta. So these are random matrices. They use shared randomness. Now they multiply, Alice multiplies A by X and Y, and Bob multiplies B. So what they get is they get smaller matrices, A prime and B prime of size k plus delta times k plus delta.
Oh, so you mean that if we have as a linear space, a matrix with rank k or bigger, then if we project it randomly on a k-dimensional space, or embed randomly a k-dimensional subspace, with high probability we keep the rank the same k, and then it's linear with respect
Yes,
to,
that's
to
exactly
A and B, and
what
we
I wanted to say.
do it. Check it kind of hashing, which is linear, and so we can.
No, we don't even need hashing. We just use trivial protocol. We exchange these matrices.
No. I say multiplying by a random matrix is a kind of dimension reduction or hashing or whatever. No, nothing serious.
So here, delta is some constant, and to get the probability less than 1/3, the probability of error, it's enough, I think, to set it to 4 or something. So it's very small.
Yeah. And you can, if need, you can repeat it by so it's.
But X and Y you generate full rank, or I
No. Any matrix, it's enough.
And if I just take them full rank, it still can be decrease the rank, or
it still can.
Yeah, but also you can generate metrics of full rank if you wish. It's not a problem, I guess.
Mm-hmm.
Oh,
But it's easier to count the number of arbitrary matrices.
Yeah, so it's very indeed very impressive simple argument. At least we can say that we understand something from, even if we are very confused by this powerful Fourier things. At least something we can understand. Yeah. It's always a good feeling.
Okay, then
what is the
we'll
meaning?
stop here.
So I have a matrix, and if I multiply it by X and Y, then the claim is that the rank will stay the same most probably. So how
it's important. No, if matrix has a rank at least k, then you will keep the rank k even if you project it to k-dimensional space. More or less on random. On random projection will also have dimension k. Have random projection on k-dimensional space will have a full rank.
So this I'm not sure, but if you the